Today I'm doing 12.1, The Goodness of Fit Test by Bradley White. Okay, some important facts to remember are these tests are regarding a probability distribution. From previous chapters, we've learned that probabilities of x must be between 0 and 1, and the Goodness of Fit test is a right-tailed test. Definition. A Goodness of Fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. This is our chi-square distribution chart. As we can see the characteristics of the chi distribution are not symmetric. The shape of the chi-square distribution depends on the degrees of freedom, similar to our students' t distribution. And as the numbers of degrees of freedom increases, the chi-square distribution will become more symmetric. What we must solve. Conducting a Goodness of Fit test. An obstetrician wants to know whether the proportions of children born on each day of the week are the same. She randomly selects 500 birth records and obtains the data shown in the table 4. Is there reason to believe that the day on which a child is born occurs with the equal frequency of all of the alpha 0.01 levels of significance? On the left we can see our graph for Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and what this is stating is it wants to see if each child is born with the same frequency at the 0.1 level of significance based on the graph or the table. Alright, step 1 for a Goodness of Fit test. We must determine the null and alternative hypothesis. The null is a statement of no difference. Basically, it's saying that the null states all of our frequencies are equal. Alternative states that if one proportion or more of are different from the others, the alternative hypothesis is correct. Our next step is to determine the level of significance. As stated in the problem, our level of significance is alpha equals 0.01. Step 3. We need to calculate the expected counts. To do this, we take the observed counts total multiplied by the probability. We then multiply the count by the probability, which will be 500 times 1 divided by 7, which gives us 71.4. This is also, keep in mind, assuming that the null hypothesis is true in that all of them are equal, all the frequencies. Step 5. We're going to calculate these test statistics. They may look like a bunch of numbers, but they're actually a formula. Basically, we're going to take the observed counts and we're going to subtract the expected counts. We're going to take that number and we're going to take the quantity squared. After we do that, then we're going to divide by the expected counts. Don't forget to take the quantity squared before you divide by the expected counts. Add those numbers up, you get 19.568. Step 6. Step 6, we're going to draw our graph. This is basically makes it easier to see what's going on. We're going to draw a right-tailed graph. We're going to see if the area is at 0.01. Our critical value is 16.812, and our test statistic falls at 19.568. Step 7. Because the test statistic 19.568 is greater than the critical value 16.812, we reject the no. Our conclusion. There is sufficient evidence at the alpha equals 0.01 level of significance to reject the belief that the day of the week on which a child is born does not occur on an equal frequency, which means that they are all different frequencies, different days of the week. And this is for you, Miss A.
Because I'm alone if you feel like a room is out.